Hello, welcome again. We are solving Indian Forest Services Mechanical Engineering paper 2 of year 2021. Question number 2C is why does a non-quasi equilibrium expansion process deliver less work than the corresponding quasi equilibrium one? A gas of mass 1.5 kg undergoes a quasi-static expansion which follows a relationship C is equal to A plus B, where A and B are constant. The initial and final pressure are 100 kPa and 200 kPa respectively, and the corresponding volumes are zero point 0.2 meter cube and 1.20 meter cube. The specific internal energy of the gas is given by regulation U is equal to 1.5 PV minus 85 kilojoule per kilogram, where P is in kPa and V is in meter cube per kg. Calculate the net heat transfer and maximum internal energy of the gas attained during expansion. So here first question is why non-quasi-static process does less work as compared to quasi-static process. So answer to this question is a non-quasi-static process delivers less work than a quasi-static process because in a non-quasi-static process the system is not in equilibrium at each step, leading to pressure variation within the system, which results in a lower effective pressure against which work is done, ultimately producing less work output. Essentially, the rapid changes in non-quasi-static process create internal imbalances that prevent the system from extracting the maximum possible work. A non-quasi-static process is a process in which equilibrium is not maintained at each step, but a quasi-static process is a process in which equilibrium is maintained at each step, and it can be assumed as reversible process. So in reversible process, as balance is obtained at each step, so uh, more work can be obtained as compared to non-quasi-static process because it results in higher effective pressure. So this is the answer to first question. Now move on to a numerical part. So the given equation is P is equal to A plus BV, where V is the specific volume, and initial and final volume and initial and final pressure are given. So these are initial pressure is 1000 kPa and initial volume is zero point 0.2 meter cube and mass is 1.5 kg. So here specific volume has to be used, so we will divide this volume by mass. So these are the initial condition and these are the 200 kPa and 1.2 meter cube and 1.5 kg are the final condition. From this we can find out A and B. So P when P is 1000 kPa, B is 0.2 by 1.5. When P is 200 kPa, B is 1.2 by 1.5. So from this we can find out B, and after that we can find out A also. So after finding out A and B, we can form the equation for P. So P is at 1160 minus 1200 B. Okay. And work done per kg is P dV integration B2 to B1. So now writing it as A plus BV, we will put the value after integration. So if we perform integration, it will be AB plus BV square by 2 and limits are B2 to B1. So this is putting limit AB2 plus BV2 square by 2 minus AB1 minus B1 square by 2. So putting A and B and B2 and B1, we get work done as 400 kilojoule per kg because B2 is in V2 and V1 are in meter cube per kg, so the work will also be in kilojoule per kg. And change in internal energy U2 minus U1. The formula for U is given as 1.5 PV minus 85. So U1 will be here 1.5 P2 V2 minus 85. So U2 will be here 1.5 P2 V2 minus 85, and U1 will be here 1.5 P1 V1 minus 85. So we subtract the two. So U2 minus U1 will be here 1.5 bracket P2 V2 minus P1 V1. We put the value of P2 V2 and P1 V1. We get change in internal energy as 40 kilojoule per kilogram. Okay. So this is U2 minus U1, and work done is 400. So heat transfer per kg is here 440 kilojoule per kg. And if we multiply it by mass, then because this heat transfer in kilojoule per kg, this work done is also kilojoule per kg, and this internal energy is also in kilojoule per kg. So we multiply these with mass, then we can get the total heat transfer, total change in internal energy, and total work. Okay. So now the equation of U is 1.5 PV minus 85. So now we have to calculate when the maximum change in internal energy comes out. So the equation of P is A plus BV. So the equation of U becomes 1.5 AB plus 1.5 BV square minus 85. For maximum U, we will differentiate it with respect to B. So it will be 1.5A, and this will be your 3B B. So B comes out as minus A by 2B. Now putting the value of A and B, we can generate B. So at this volume, the internal energy will be maximum. So first calculating pressure at this, and then putting the pressure in this equation. So U max will come out as 335.49 kg per kilojoule per kg. So we multiply by bias, then the maximum, total maximum change in internal energy.